Hi guys, so today we're working on 13.1 theoretical probability of simple events. Now, if you watched my video on actual probability, this is going to sound super familiar. So basically what theoretical probability is, if I tell you how much of something I have and how often something will occur, I can then guess how probable the outcome is. So for something like coin flip, I have heads and I have tails. If I flip it, I will land on heads 1 out of 2 times. I will land on tails 1 out of 2 times. So theoretically, for every 2 times that I flip it, I'll land on heads once and I'll land on tails once. Theoretically, that's how it should work. Mathematically, that's how it should work. If I have something like this, if I have a spinner, and we're going to pretend that all of those are the same size. I realize they don't really look the same size, but we're going to pretend that all of those are the same size. And I have purple, and I have orange, and I have pink. Okay? We're going to pretend that each of those is the same size. My probability of landing on purple is 1 out of 3 chances. I have 3 chances. One of them is purple, so that is my probability of landing on the purple. My probability of landing on the pink is also 1 out of 3 chances, and my probability of landing on the orange is also 1 out of 3 chances. Now, if I had something that was more like this, we do a lot of things where we have spinners, and okay, so I just cut that one into 8 pieces, and I'm going to put a star into this one, and I'm going to put a star into this one, and I'm going to put a star into this one. So if I asked you what the probability of us spinning and it ending up on a star is, I have 1, 2, 3 stars out of 1, 2, 3, 4, 5, 6, 7, 8 chances. So 3/8 is my probability. How many do I actually have out of how many total chances? So 3/8 is my probability of landing on a star. 1, 2, 3, 4, 5 out of 8. 5/8 is my probability of not. So this is a star. This is not. Okay? So I have a higher chance, a higher probability of not landing on a star than I do of landing on a star. Does that make sense to you? This is how we actually write this out. Okay? So let's go look at, just a second, let me see if there's anything else that I need to give you notes on. I don't think there is. Okay, so the last thing that we need to talk about is the difference between experimental and theoretical. So experimental means I actually tested it. I actually tested it. Okay, this is what I came up with when I actually tested it. Theoretical is what it should be. What it should be. So when you go to like a, let's say that up here, you want a prize every time that you landed on the star and you're going, okay, I'm going to do 8 spins. You should win 3 prizes. But in actuality, you might not win 3 prizes. You might win 8 prizes. It could land on a star every single time. Or you might win no prizes. It could never land on a star. You might only win 1 prize. The way that theoretical probability works is saying if all other things are equal, this is how often overall it will occur. So we're not talking about in 8 times. We're not talking about in 20 times. We're not even talking about in 100 or 200 times. We're talking about if I kept trying. If I kept trying and trying and trying and trying and trying and trying and trying, like 5, 6, 7, maybe even a couple thousand times, 5, 6, 700, maybe even a couple thousand times, then you would see that it's about 3 out of every 8 times you get a star, and about 5 out of every 8 times you don't. You, however, doing just 8 turns will not be guaranteed to get those results. Those results show up after an insanely long period of time. So if we're trying to figure out for a game or something how much of a chance there is of you winning, we don't look at the 3 times that you're playing the game. We look at the 16,000 times that anyone in the world, all put together, is playing the game. So that is the difference between experimental and theoretical. Experimental is I actually tested it and this is what I got. Theoretical is this is what it should be. And this is what, if I make the sample big enough, this is what it will be. Okay, so let's move on to the page 399. Okay, so it says, in previous lessons, you found probabilities based upon observing data or experimental probabilities. In this lesson, you'll find theoretical probabilities. So we're looking at the spinners, which are on the page on 399. At a school fair, you have a choice of spinning spinner A or spinner B. You'll win an MP3 player if the spinner lands on a section with a star on it. Which spinner would you choose if you want a better chance of winning? So spinner A has a number of outcomes of, we literally just count how many segments there are. There are 8 segments on spinner A, whereas spinner B has, it looks like 16. Yeah, spinner B has 16 segments. Okay, so I'm just making the quick and dirty chart right there. The number of sections that have stars in spinner A is 3. The number of sections with stars on spinner B is 5. So the probability of winning in A is 3 out of every 8 times, or 3/8. The probability of winning in B is 5 out of every 16 times, or 5/16. So we are going to compare the ratios of spinner A and spinner B. The ratio of spinner, okay, so it's hard to compare these the way that they are right now because they have different numbers on the bottom. So let's make it easier. Let's go over here and let's multiply the 8 times a 2 to make that a 16. Whatever we do to the bottom, we have to do to the top. 3 times 2 is 6, and 8 times 2 is 16. So we're actually comparing 6/16 to 5/16. So we can tell just from there that spinner A is greater ratio than spinner B. So I should choose A to have a better chance of winning. because it would end up being 6 out of every 16 times instead of 5 out of every 16 times. For number 1, theoretical probability is a way to describe how you found the chance of winning an MP3 player in a scenario above. Using the spinner example to help you, explain in your own words how to find the theoretical probability of an event. Well, you can explain it how you want to. My words for it are theoretical probability is how many times something has a chance of happening over how many chances there are available. Going on to the next page, calculating theoretical probability of simple events. Theoretical probability is the probability an event occurs when all the outcomes of the experiment are equally likely. Probability can be written as a fraction, as a decimal, or as a percent. For example, the probability that you would win with spinner B is 5 out of 16. You could write it as 3,125 10,000ths, or 31 and 2500ths%. A bag containing 6, I'm on example 1 now. A bag containing 6 red marbles and 12 blue ones. You select one marble at random from the bag. What is the probability you will select a red marble? So we have 6 red marbles out of a total of 18 marbles in the bag. So 6 over 18, we then divide out the 6 from both the top and the bottom, which leaves us with 1/3. Number 2, we're going to roll a number cube 1 time. What is the probability that you will roll a 3 or a 4? Okay, so a 3 or a 4. How many numbers is that? 2. How many sides does a die have? 6. 2 out of 6. I have absolutely no idea why they gave us such a long line for it. That's completely nonsensical. I'm going to divide out a 2 because I can, which gives us 2 divided by 2, which is 1 over 6 divided by 2, which is 3. So 1/3. That's our probability. Number 3, how is the sample space for an event related to the formula for theoretical probability? Okay. So the sample space for an event is we're talking about the experimental again. So is how often something does happen versus how often it should happen. Now, I realize that this is a hard thing for a hard concept to get across. It always has to do with how big your sample size is. So for something like flipping a coin, if you flip a coin 100 times, you will get very, very close to 50 heads, 50 tails. You need to do 100 times with just those two choices, though, to get there. If you are rolling a die, however, and you have 6 possibilities, you have to go at least like 500 times to get there for every single one of them popping up about 1/6 of the time. So, okay, let's go over to 401, comparing theoretical and experimental probability. Now that you have calculated theoretical probabilities, you may begin to wonder about theoretical and experimental probabilities. Compare. 6 students are performing in a talent contest. You roll a number cube to determine the order of the performances. You roll the number cube once. Complete the table of theoretical probability for the different outcomes. Okay, so theoretically, 1, 2, 3, 4, 5, 6. Theoretically, there is a chance of me rolling 1 the first time, a 1 in 6 chance. Rolling a 2, a 1 in 6 chance. Rolling a 3, a 1 in 6 chance. Rolling a 4, a 1 in 6 chance. Rolling a 5, a 1 in 6 chance. Rolling a 6, a 1 in 6 chance. There is the exact same probability for every single number being rolled. Step number 2, predict the number of times each number will be rolled out of 30 rolls. So 1, 2, 3, 4, 5, 6. Now, this is out of 6 rolls. What we have up on top is out of 6 rolls. I want it out of 30. 6 times what gives us 30? 5. Whatever I do to the bottom, I need to do to the top. So I'm just going to do it one time over here because they're all exactly the same. 5 equals 30. So I do times 5. 1 times 5 is 5. So 5 times out of 30, I'll get a 1. 5 times out of 30, I'll get a 2. 5 times out of 30, I'll get a 3. 5 times out of 30, I'll get a 4. 5 times out of 30, I'll get a 5. And 5 times out of 30, I'll get a 6. I will get each number 5 times. Now the next one is I need to actually roll the number cube and complete the table for the frequency of each number and find its experimental probability. I am going to come back to you after I roll all the dice. Just a second. Okay, so I rolled all the dice. I did the tally chart right there. I'm going to write down the actual numbers that I got for each of these. So for 1, I got 7 out of 30. For 2, I got 4 out of 30. For 3, I got 3 out of 30. For 4, I got 5 out of 30. For 5, I got 6 out of 30. And for 6, I got 5 out of 30. So only 2 of them did I actually get the 5 that I was predicting. Although 6, 3, 4, and 7, they aren't that far off. They're not like way huge, way far off. So we're going to look at the tables we completed. How does the experimental probability compare to the theoretical probability? Well, basically, the experimental probability is more the experimental probability is more varied. The numbers are different. So here in theoretical probability, I end up with all the numbers being the same. Here, they're all over the place. Number 5, by performing more trials, you tend to get experimental results that are closer to the theoretical probabilities. Combine your table from step 3 with those of your classmates to make one huge table for the class. How does the class experimental probabilities compare with the theoretical probabilities? So if we were to do that, if all of us were to put all of our information together and combine all of it, we would end up with somewhere in the ballpark of 30 times 20, 600 points of data. If we did that, it would be more than 600, it'd probably be closer to 700. If we did that, we would then have very, very close. How does the class experimental probability compare to the theoretical? The class put together is almost, it would be identical. Is almost identical. It would probably still be off by a little bit. There's still a factor of error. It depends on how people actually roll the dice and that kind of thing. But by and large, we would end up with the same thing. Could the experimental probabilities ever be exactly equal to the theoretical probability? If so, how likely is it? If not, why not? So what I'm going to say for this one is probably not. For number 4, probably not. And then the reason for that is there's always chance in there. There's always bad luck. There's always good luck. There's always it happening. It almost is never exactly the same. When you actually test it out, you almost always have slightly skewed results. And I mean very slightly. It's why when they talk about statistics in science, they sit here and they say, well, it's pretty much this. Let's round it. And your actual results might be a teeny tiny bit different than this, but we know enough that we can round it anyway and say this is about what you're going to get. Probably not. The actual world sometimes has, and I'm going to put down odd things happen. Is it possible that you can flip the coin 1,000 times and end up with an exactly 1 out of every 2 times it flipped to what it was supposed to? Absolutely. That is definitely a possibility. Is it likely? No. It's not likely at all, actually. Okay, so I'm going to go down to the guided practice. If you need to pause this, pause. Okay, so guided practice number 1. At a school fair, you have a choice of randomly picking a ball from basket A or basket B. Basket A has 5 green balls, 3 red balls, and 8 yellow balls. Basket B has 7 green balls, 4 red balls, and 9 yellow balls. You can win a digital book reader if you pick out a red ball. Okay, so again, we have basket A and we have basket B. How many balls are inside basket A? That's our total number of possible outcomes. 5 plus 3, which is 8, plus 8, which is 16. In basket B, we have 7 plus 4, which is 11, plus 9, which is 20. So basket A has less balls in it than basket B does. How many red balls are in basket A? 3. How many red balls are in basket B? 4. So we now need to put this together and figure out number of red balls. How likely are you to get a red ball? 3 out of 16 chances to get a red ball in basket A, and 4 out of 20 chances to get a red ball in basket B. We could also divide out that 4 so that we would end up with a 1 out of 5 chance in basket B. Yeah, basket A has 16. Okay. So then, which basket should you choose from if you want a better chance of winning? We cannot look at these right now and just tell. We need to figure out which one actually has it. And to do that, we need to have common denominators. So I am going to do 3/16 times 5. And I'm going to do 1/5 times 16. So let me see. 3 times 5 is 15. Over 16 times 5, getting out my calculator, 80. 1 times 16 is 16. Over 5 times 16, which is 80. So we see here, basket A has 15 out of 80. Basket B has 16 out of 80. So which basket should we choose from? We should choose from basket B, because that one is better for us. Number 3, a spinner has 11 equal-sized sections marked 1 through 11. We spin once and land on an odd number. Okay, let's see, how many odd numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 6. So actually, let me pick a different color. So 6 out of 11 for an odd number. Number 4, you spin once and land on an even number. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 5. 5 out of 11 chances that I'm going to land on an even number. So it is more likely I will land on an odd number than an even number. Okay, next part. I keep changing which marker I'm picking up. Number 5. What is the theoretical probability? Okay, so I'm rolling a number cube. What is the theoretical probability? You will roll either a 3 or a 4. 3 and 4, that's 2 chances out of 6 sides on the die, out of 6. So I'm going to divide out the 2, which gives me 1/3. That's my probability, 1/3. Number 6, suppose you roll the number cube 199 more times. Would you expect the experimental probability of rolling 3 or 4 to be the same as your answer in exercise 5? Number 6 is no. No, I would likely end up very slightly different. Because you just always do. You end up very slightly different. Not a ton different. Not so much different that you're going, oh my goodness, this is weird. But just a teeny tiny bit different. And finally, number 7. How can you find the probability of a simple event if the total number of equally likely outcomes is 20? Okay. Put the number of times the outcome you want occurs over 20. That's how you do that. Okay. So that takes us to the independent practice. I think you should be able to do it. So have a good day. I'll see you later. Bye-bye.